rat, and the flea on the rat can bite the human, and that's how the human gets the plague. Symptoms of the plague include swollen glands, black spots on the skin, and extreme pain. The plague in Asia wiped out 1/4 of the population. This was a pandemic in the early 1900s. Plague still occurs, by the way. Modern antibiotics and healthcare will kill the bacterium. Then we have malaria. Malaria comes from a mosquito. It's a parasite that actually lives on the mosquito, a parasitic protist, actually. It spends one stage of its life inside the mosquito and another stage inside a human. Every year, 350 to 500 million people in the world contract the disease, malaria, and 1 million of them die, mostly children under 5. The U.S. still has around 1,000 cases per year from travelers. DDT, remember that chemical, used to eradicate them, but we are no longer allowed to use that because of all the other negative environmental health effects. Then we have TB, or tuberculosis, which is a bacteria. It's highly contagious, and it primarily infects the lungs. If you have it, your coughing spreads germs big time. These germs persist in the air for several hours, unlike many other germs. You cough up blood. About 2 million people die per year of tuberculosis. You can be treated with antibiotics for it, which isn't a problem in a more affluent or highly developed society because we have antibiotics. These medicines are not affordable in less affluent countries, or they're not seeing a doctor at all. New strains have come about, though, due to the antibiotic resistance, and these are much harder to kill. All right, so emergent diseases. These are infectious diseases. These are either very new, like mad cow disease, or they're uncommon, like we haven't seen them show up on our radar for a long time. One emergent disease usually occurs each year. The year of 2014 was Ebola. So just some notes, you need to know these types of things about these diseases. By the way, the little red dots that are on there on the map here, these red dots are not necessarily the place of origin. It's just where we're most likely to see that disease show up and become epidemic, or start with the epidemic. So we have HIV, human immunodeficiency virus, and this causes a weakened immune system. About 33 million people are infected today. 25 million have died from AIDS-related illnesses. Then we have Ebola. You have about 2 weeks to live once you contract it. It's highly contagious. There's no medicine or treatment, and it causes a painful death. It's a virus. The source, according to your book, is unknown, but probably the Congo near the Ebola River. Primates related, and we have found now, especially in the 2014 case, mammals such as bats are carrying the Ebola virus, and it is transmitting to humans. Primates die too, so they're probably not the actual long-term source or carrier because they are also dying from it. Then we have mad cow disease, where the cow goes cuckoo. It's literally going neurologically cuckoo and dies. You don't eat cow meat from infected cattle. The proteins in the brain, which are called prions, actually mutate, and the cow can't transmit to a cow unless it eats infected cow. Humans can carry the disease for years before it displays itself, so it's more chronic, not acute. Cooking the meat does not kill the prions like you can cook the salmonella out of a chicken. Symptoms in the human body may not occur for years, but we are now no longer allowed to feed cows to cows. Then we have bird flu, H1N1, H5N1, lots of versions, also known as Spanish flu. It jumps from birds to people. Wild birds usually are fine with it, but duck and chickens will die. Virus jumps from birds to people. Then we have the West Nile virus. Mosquitoes transfer through birds. Blue jays, crows, robins are highly susceptible to this. We must kill mosquitoes because they're the ones that transmit it. They're the vectors here. Remember the word vector. As climate change occurs and mosquitoes move more northward, so does the West Nile virus. So we need sanitation, we need education, we need people to have balanced diets, we need money for medications, and we need vaccines to help eradicate these diseases. In the United States, the West Nile virus first appeared in 1999. We started using efforts to control the mosquitoes to reduce the prevalence of the disease. All right, so this is where we start toxicology. So we're leaving the biological risks and we're going to go into chemical risks. Toxicology is the study of chemical risks. Our modern society had developed an incredible array of chemicals to improve human life around the world, including pharmaceuticals, insecticides, herbicides, and fungicides. Yes, they're beneficial to human health and food production, but often they form byproducts in manufacturing that are harmful. They also can be toxic in higher doses or have unexpected and harmful side effects. Listed here are the categories of chemicals causing harm to humans. These are categories, the categories of chemicals that cause harm. You need to be able to pronounce them so you don't sound like a fool. So say them each out loud after I do. Neurotoxins, neurotoxins. Carcinogens, teratogens, teratogens. Allergens, endocrine disruptors. Teratogens, neurotoxins, teratogens. Okay, which one here has to, if you get exposed to this chemical, it causes fetal alcohol syndrome? A teratogen. Which one here, if you are exposed to secondhand cigarette smoke, causes harm to humans, like cancer? Carcinogens. Get it? So toxicology, study of chemicals and their risks. All right, this is in your book. I cannot read this whole thing to you. You need to know it really well. You need to know what's the source for lead, what's the effect. We're going to glance at this, actually. I'm going to open this up. Come on, open up. All right, so lead we know already. We know most of these already. Lead comes from paint or gasoline. Mercury comes from coal burning and eating too much fish, especially the fish that are higher in the trophic levels. And then you need to understand what category each of these falls under. That's what they mean by type. So lead is a neurotoxin. So what you should do is you should study this chart. It's a neurotoxin. Then you should go back here and you should remind yourself that a neurotoxin is something that disrupts the nervous system. So what does that mean if it disrupts the nervous system? Well, in this case, you get too much lead in your system. You're going to have impaired learning. You're not going to be able to think right. You won't be able to process your reading and your math. So it's almost like you're dumb. It's a neurotoxin, impairs the nervous system, causes disorders, and can even cause death. Mercury, a neurotoxin, damages your brain, does not allow you to process right, damages your kidneys and liver and immune system. You get it from coal burning. Arsenic, from mining in groundwater. Arsenic is a carcinogen. This is the category that arsenic falls under. It causes cancer. Asbestos causes cancer. PCBs cause cancer. Radon causes cancer. Alcohol use a teratogen. Atrazine. Atrazine is an endocrine disruptor. What does that mean? It makes males more feminine and causes low sperm counts, which means males show female traits. Where do you get exposed to this endocrine disruptor? In a weed killer. Atrazine is in our weed killers. It's an herbicide. Then there's DDT. Also causes feminization of males. Thins eggshells of birds, specifically the American eagle. This is DDT, was the insecticide that actually almost caused the complete extinction of eagles. Then you have phthalates. You must know this by heart. Make sure you study it. Okay, the decline of lead in children, look at the dotted line. The dotted line is the safe level for lead. Remember that lead is a neurotoxin. It causes neurological impairment, and it's toxic. It's toxic to you. So what you should understand from this is not how to read the bar. You should understand the decline of lead found in the blood of children. So now that we know about it, we've been able to be more proactive and more educational. This is an example of a teratogen. Phthalimide was a medicine. Whenever a woman got morning sickness, she was given this medicine to help her feel a little better so she could get through the day, and phthalimide was the medicine she took. It took a couple of years for doctors to finally realize, oh my God, there's all these babies that are coming out and they're deformed. They literally have mutated in their development. Well, that's what a teratogen does. Then we have endocrine disruptors. I'm not going to read this whole thing to you, but it has to do with your hormones not being able to work and function the way they should. For example, male animals normally make estrogen and then convert it to testosterone, an important hormone for male reproduction. Some endocrine disrupting hormones are thought to interfere with this process, causing less testosterone to be produced. And as a result, these males can have low sperm counts, and eggs may even develop in their testes. All right, so can you name a neurotoxin? Here they are. Can you name carcinogens? Try and name 3. Here they are, carcinogens. That's how you test yourself on this chart. Make sure you know these things and make sure that you understand what they do to you. All right, so I don't know why I'm showing you that. That was something they were going to do for me. In the U.S., the Environmental Protection Agency authorizes and regulates many chemicals by the Toxic Substances Control Act of 1976. In the United States, the EPA authorizes and regulates the chemicals through a law or legislation called the Toxic Substances Control Act of 1976. And what do they do with that? They look at and do studies. They're called dose-response studies. They look at lethal doses and LD50s, LC50s, lethal concentrations. So we're going to study charts like this so you can understand. I'd like you to make sure that you copy this stuff down. Lethal dose, lethal concentration. So LD50 means that it's going to kill whatever this drug is, whatever the concentration is, it's going to kill 50% of the individuals exposed to it. Lethal concentration means the same thing, it's just usually a liquid form. Effective dose causes 50% of animals or humans to display therapeutic results. Think of Tylenol. When does it get rid of your headache? So an effective dose 50 means 50% of the people. Follow this curve. 50% would be this line. Oh, this dosage is the dosage that actually the effects take place. If we're looking at something that's a lethal dose, we're looking at the dosage that kills 50%. Then we have something called the threshold dose. This is where it can the dose where the effect can be detected. So the effect is that it can get rid of your headache, or the effect is that it makes you sleepy. So know what these are, and this is all related to the study of chemicals and their effects on humans. Now here's another example of an LD50 study. Okay, remember, they're used to determine the dose of a chemical that causes 50% death rate. That's LD50. Typically, the study produces this S-shaped curve right here. This is the 50% line, so 50% of the population would die if they're given this approximate dose, okay? And we don't have units here because they're just showing you this curve. This curve tends to be what we find with most chemicals when we first set up our bioassay or our LD50 experiment, okay? Percent mortality is how many people die. So typically we like to go down to the 10% dose when we start studying them in more depth. So for us to calculate safe doses, when like a rat is fed increased amounts of a chemical, the amount of mortality will increase. Do you understand that? We're going to do this in class. We're going to do a lab with it. Here's a researcher conducting a toxicology study or an LD50 study. We're doing something like this in class. All right, you also need to know about synergistic interactions. This is when you have two risks, but when those two risks are together, they cause more harm than if they were separate. So being exposed to asbestos, yes, causes cancer. So you have, let's say, a 25% chance risk of getting lung cancer. And then if you smoke cigarettes, let's say you have a 25% risk. Well, if you're exposed to asbestos and you smoke tobacco, maybe the synergistic effect makes it, because it's synergistic, makes it a 75% chance that you're going to get cancer rather than a 50% chance. So the study of all of this is called epidemiology. And there's two types of studies done in epidemiology for us to learn about what chemicals actually are risky. We have the retrospective studies and we have the prospective studies. Retrospective studies are ones where we look back in time. So retrospective studies, one really big one that we look at happened in India. This is where there was a pesticide plant, and they were making pesticides which are incredibly volatile, flammable, explosive industries, and it blew up in 1984. And the survivors of the accident have all kinds of long-term health effects, and so do the children that they have. So even teratogenic effects. That's a retrospective study. I'll read this while you look at the chart. In 1984, a massive release of a chemical gas killed and injured thousands of people, and this shows the retroactive study following the survivors of the accident and the long-term health effects. We can't just give humans chemicals and use them as our test rats and say, hey, we want to find out what this chemical does to you. We can't do an LD50 study on purpose, wondering how many humans it's going to hurt. So the only way sometimes that we can find out if the chemical was harmful to a human and what effects it had was looking back at the humans that were actually exposed to a chemical by accident. That's what a retrospective study is in the field of epidemiology. So it's all like a forensic investigation to be in epidemiology. Okay, these are the different routes of exposure for getting exposed to different chemicals. You can get chemical exposure through water, through air, through food, through soil, and your fetuses and babies can also get exposed. So you need to know the difference between bioaccumulation and biomagnification. We've talked about it 2 times. Here's your reminder of bioaccumulation. This is an increase in concentration of a chemical within the organism itself over time. That means your tissue doesn't break down the chemical, and every time you're exposed to it, it just builds up and builds up and builds up and builds up. It accumulates, it accumulates, it accumulates in the system, which increases the concentration of that chemical, which at one point, one exposure might not be toxic. But when you accumulate an increase in concentration with a chemical, that accumulation then can become toxic and then can cause cancer and cause all these harmful human health effects. So the movement of chemicals in the environment depends on its solubility in the human body. So some chemicals store really well in your oils or your fats in your body, and some store better, or they break right down in water. Vitamin C, for example, does not store well in the body. It's very soluble in water, and you're going to run it right through your body. Some store really well in soils, and soils are more oily or fatty. Some store better they will last for a long time in groundwater. Then we have, instead of bioaccumulation, which accumulates in one body over time, then we have biomagnification. That's where we move up the food chain. So in biomagnification, I want you to watch the DDT here in the water and look at our parts per million. It's so small, it's in the water, and it's that many parts per million. Then the plankton will ingest the DDT, and it's accumulated in the plankton body over time, higher in concentration. They don't break it down. No big deal though, because it's in the plankton. But then the stickleback, this fish, eats the plankton. So now it's what has accumulated here is now magnifying up the food chain. So the concentration is increasing because this fish doesn't eat just one plankton. This fish eats hundreds of plankton a day. So it's accumulating in the fish, but because it's moving through the food chain and it's concentrated and the fish is eating more than one, it's not just transferring, we're eating several. Now we are magnifying. Then the flounder eats the stickleback, and the flounder is eating this. But it's not just eating one of these, it's eating many of these. And that increase in concentration is also magnifying because he's eating many of these per day. And then the poor osprey is getting this many parts per million of the DDT. And remember, this acts as an endocrine disruptor for the osprey's eggs. So know the difference between your biomagnification and bioaccumulation. All right, we have persistence, and that's how long something's going to last in the environment. Look at this chart. So we have, these are common chemicals. Roundup is an herbicide. It's a weed killer that you've probably all heard of. Roundup has a half-life of 7 to 70 days in water. Okay? Then we look at radon gas. Radon has a half-life of 4 days in the air. So that's how long it lasts in the air. Half of it will be gone within 4 days when it's exposed to the air. half of it will be gone. That's what half-life means. And then half of that half will be gone. Just think about the 75%. DDT is incredibly persistent, lasts 30 years. PCBs, your polychlorinated biphenyls, which are in plastics, last 8 to 15 years in water. That's not good stuff. And these are endocrine disruptors as well. So then we do things in the human world, in human health and risk assessment. We do something called a risk analysis. And I want you to read about this and learn how to understand it on your own rather than me talking about it. A risk assessment starts with identifying what the problem is and then finding out what the toxicity is, the dosage and the responses to dosage, and then how long the exposure needs to be. It could be just one of these things in the assessment, or it could be all of them. Then we have to determine, and the EPA helps with this a lot, well, we're going to be exposed to this stuff, so what's acceptable and what should we make illegal? What should we make punishable? What should we legislate? And that's why politics is very involved in this. And then we have risk management. All right, so now we know what can harm people. Now we need to educate them. Now we need to set a law in place so that we can put permits in there, or we can penalize any companies that are putting something that is an unacceptable level into our water or into our air. That's risk management. So we have the assessment, which is identifying the hazard and what the toxic doses are, what the exposure is. Then, okay, now we know all about it. Now we've got to figure out what to do with this information, what's acceptable to us and what's not acceptable, and then managing it. So we've decided what's acceptable. Now we're going to have to implement this and hold people accountable. This is part of what we call the risk analysis cycle. I think I stole this from somewhere else, but this is the probabilities of death in the U.S. So in the United States, there's a 1 in 5 chance that you will die of heart disease. Isn't that lovely? There's a 1 in 7 chance that you will die of cancer. There's a 1 in 24 chance that you will die of stroke. Now that's just on average. If any of this stuff runs in your family, your chances, your probabilities are even higher. There's a 1 in 84 chance you could die in a motor vehicle accident. Look at all these other ones. Oh, there's a 1 in 117,000 chance that you could die in an earthquake. I think you have a better chance of dying in an earthquake than you do of winning the big lotto. That's pretty sad. So we also have things called a qualitative risk assessment. You do need to understand the difference between qualitative and quantitative. This is where qualitative, we're just making a judgment and we're talking about relative risks, okay? So I'm going to read this to you, sorry. The statistical likelihood of an event occurring and the probability of the event causing harm is called the probability. You really do need to know that because we use that word. Qualitative means making a judgment. Qualitative, making a judgment. Quantitative is when we look more numerically, okay? Risk is the probability of being exposed to a hazard. Sorry about the bell. So, for example, it's riskier to fly on a commercial airline for 1,000 miles per year or to eat 40 tablespoons of peanut butter per year, okay? Oh, and you know what? Both are a 1 in 1 million chance of dying. Just saying. All right, so we have the Stockholm Convention. This occurred in 2001, where a group of a whole bunch of nations got together in Sweden, and they reached an agreement where they were like, okay, we need to start restricting some chemicals and their use. So 12 chemicals were banned. Some of the chemicals included DDT, PCBs. They were banned according to the Stockholm Convention. Notice that we had 127 nations, and that's not the world nations, and not everybody agreed to everything, and not everybody is holding their end of the bargain. But it was an international agreement. So if you're ever asked about international versus national, be careful. International agreement. This is not federal. Federal is just national. Okay, so you need to understand the precautionary principle. I'm going to give you a moment to just read this. The precautionary principle, okay? So that you can understand how testing is required and how we determine if a product is safe. So here's where the safe consumer product is. Here's where the safe consumer product is. And this is the innocent until proven guilty principle. Just follow the arrows. If I read everything to you, I don't think you're going to get as much out of it. And follow them in different directions. So notice sometimes products become available and we call them safe, even though There's been no regulations and bans, and they're called safe, and that's why we have little quotes around them. The precautionary principle. Take a minute to keep following it. So these are basically two different philosophies, and this is all about managing risk. So the innocent until proven guilty principle requires that researchers prove harm before the chemical is restricted or banned. They have to prove that it harms. The precautionary principle requires that when there's still scientific evidence that demonstrates a plausible risk, the chemical must then be further tested to demonstrate that it is safe before it can continue to be used. It's based on, the precautionary principle is based on the philosophy that when a hazard is plausible but not yet certain, we should take actions to reduce or remove the hazard. The risks of asbestos dust are shown here. Despite nearly a century of studies on the risk of asbestos dust to human health, only recently have workers been required to go to great lengths to prevent exposure. So this is just an example of how we are combating malaria in countries where that biological risk still exists. All right, that's the end of our presentation for Chapter 17, Human Health Risk. I hope you enjoyed your 27-minute video cast. Please study carefully and know the names of all your chemicals and biological risks.